Hi everyone, welcome back to Chem Corner. Yes, we are continuing the FRQ discussion. Today we can do with the FRQ question number 2. Let's see. Here we go. So the first question is about combustion analysis, right? Okay. A student combusted a sample of ascorbic acid CXHYOX and they were given 0.24 CO2 moles of CO2 and a 2.883 grams of water. Okay, calculate the number of moles of water. It's very easy, right? You can just do what 2 point given mass divided by molar mass of water. Molar mass of water is 18.02. So that's all. I think 0.1600 mole. Okay. Then second question. Mole ratio of carbon and oxygen is 1:1 for ascorbic acid. Okay. Then you have to calculate the empirical formula. Okay. So what is the carbon number of moles? Yes, 0.244. Why? 0.2400. Why? Because that many CO2 is there. 1 mole CO2 contain 1 mole carbon. So this is the same number of moles of carbon. What about oxygen? Yes, that is also the same. They were given it's 1:1. So the same thing. What about hydrogen? What is the number of moles of hydrogen? At the top we already found 0.1600 moles of water is formed. So one water contain 2 hydrogen. So 0.16 moles contain 2 times 0.16 mole, that many moles of hydrogen. Okay, so that is 1.3. Oh, sorry. That is 0.313196. Okay, just multiplied by 2. Correct? Okay, so this many number of moles are there. Then what to do? We need the relative, like the ratio. So n divided by smallest number, isn't it? First one, we are converting the, usually the gram will give a gram to the number of moles. Okay, and then number of moles divided by lowest number, smallest number of moles. So here 0.244 is the smallest one. So 1, and when you divide this one, you will get 1.3. So 1.3, you don't have the permission to round it like 1. That is wrong. So what to do? You have to multiply with some constant. In that way, you can get rid of this fraction number. Okay, this point number. Okay, so what is that number? If 1.5, you can multiply with the 2. Similarly, what is the multiplier using here? It's 4. 4 is, sorry, 3 is the multiplier used. Isn't it? Yes. 3 is the multiplier we are using. So everything have to multiply with the 3. So that what we got. Here it is. So 3, C3 and oxygen is also 3 and 1.3 times 3 it is 4. So what is this empirical formula? C3H4O3. Clear? That is the thing. Okay. Then the question, second question, they were given that ascorbic acid titration curve with a strong base. Okay. And the amount ml of 10 ml is the first one, ascorbic acid, and the other one you can take it from the graph. Okay, calculate the molar concentration of ascorbic acid solution. Very simple. How do you calculate from the graph? You can just take the equivalent point, right? At equivalent point, you can apply M1 V1 is equal to M2 V2 because this is 1:1 ratio. So no issue with the M1 V1 is equal to M2 V2. Or you can calculate separately number of moles of NaOH you can calculate and the ratio is just 1:1. See, how do you know? See the thing, HAC gives 1 H3O plus. It shows it is a monoprotic acid. Okay, so that's it. And the NaOH is, as you know, it's a mono basic. Okay, that's all. So you can calculate M1. M1 we don't know, that is ascorbic acid concentration, but volume of ascorbic acid 10 and the molarity of base 0.055 and the volume, see, at equivalence point volume you need to take, so 16. Okay, then what is M1? You can just calculate this one. So you will get M1 as 0.088 I got it. That many molarity will be the thing. Okay, and the second question, from the titration curve determine approximate pKa. So very important point, in a titration curve, half equivalence point. So what is the half equivalent point? See, equivalent point is 16. So half equivalent point is 8 at volume 8. Okay, so what is the corresponding pH? Equivalent point pH will be, it's not exactly 4. You can take 4.1, isn't it? Okay, so pH is equal to pKa at half equivalence point, isn't it? So pH is equal to pKa. So what they were asking is pKa. So 4.1. Equivalence point pH will be the pKa value of the acid. Okay, right. And the third part, what will be the ratio of base over acid when pH is equal to 4.7? So see the pH 4.7. pH 4.7 means it is definitely below the equivalence point, right? Below the equivalent point, the system is buffer. Okay, if you not know the concept, you just watch my video about buffers and this titration. There is a titration video. You can see that one. Okay, so here what is the thing? Before equivalent point, the system is buffer. So you can directly apply the buffer equation, like Henderson equation. What is that one? pH is equal to pKa plus log base over acid concentration. Isn't it? Okay. So what is this ratio? pH is given 4.7. pK we got 4.1, I think. Yes. And the log, this one. So what is the thing? Log of base over acid. Okay. Right. So 4.7 minus 4.1, it's 0.6. So anti-logarithm you need to take. So 10 to the power of 0.6 will be the base concentration over acid concentration. Okay, so that is the thing, right? Then the next question is, okay. Then the next question, this ascorbic acid reacting with the I3 minus, okay, and the reaction is given, and see the rate, okay, something related to kinetics is given. Okay, so trials are there and the different concentration is given and different rates are given. And yes, see, as I told you, they were given all the answer. You don't want to even calculate the rate law. Okay, they were given the rate law is this one, and what you need to do is explain how the data and the table support. It's a first order with respect to ascorbic acid. Okay, right, that's all. So how do you support it? See the trials. When you are taking one trial 1 and 2, see ascorbic acid concentration is same. So don't want to take 1 and 2. What about 1 and 3? Ascorbic acid is doubling, right? Since it is doubling, the base is 2. Doubling means 2. And 2 raised to something is there that we don't know. That is the power of ascorbic acid, right? In rate law is equal to what? Rate thing. Is that okay? Like here, the I3 minus, there is no change in concentration. So that will be just 1. And what about the rate? When ascorbic acid doubled, what happened to the rate? Rate is also doubled. Did you notice that one? See, ascorbic acid doubled at that time. Rate is also doubled. So since it is doubled, you can write 2. Okay, 2 raised to x is equal to 2. So what is the x value? Is 1. Okay, so you can show this one. Okay, HAC is ascorbic acid. When it's doubled, rate is also found to be doubled, so that it is understood it's a first order reaction with respect to ascorbic acid. That's all. Then you need to calculate the rate constant. So you know the rate law, so you can take any of the trial. So I'm just taking first trial. According to that, see the equation, rate is equal to K is there and ascorbic acid concentration is given for the first trial 0.450, and for the I3 minus it is 1.200, and the corresponding rate is equal to, yes, first one 2.457 times 10 to the power of minus 4. So the K value will be, yes, you can just do the calculation. And what I got is 4.55 times 10 to the power of minus 4. That's the thing. Okay. And a unit is very important. What is the unit of rate constant? Unit, how do you calculate? Molarity raised to 1 minus n second inverse. What is this n? Order of the reaction. So here see the rate law. Rate law order means the power of the rate law. Okay, the sum of powers of the rate law. So here ascorbic acid raised to 1, I3 minus raised to 1. So 1 plus 1, 2. So molarity raised to 1 minus 2 means minus 1 second inverse. So that will be the unit of K. Okay. And again, want to take care about signin figure. Here 3 signin figures. So your answer should also contain 3 signin figure. Okay. That's all. And the last question now for this one. Triiodide ion I3 minus is significantly more soluble in water than in elemental iodine. Okay. So identify the intermolecular force between I3 minus and water, which is not present between I2 and water. Okay. So what is this one? I3 minus, they were given the Lewis structure also. So see, negative charge is there. What does it show? So what is the intermolecular attraction? IM of between I3 minus and water. I3 minus, is it polar? I3 minus is it's a polyatomic ion. So definitely this is an ion, not even polar. It's polarity at its most. Okay, polarity when it hit the utmost level, that is what we called ion. So iron and what is water? Water is a polar molecule. So here what is the interaction? Ion dipole interaction. Ion dipole interaction is, what's the interaction between what water and this one? Clear? Ion dipole interaction is between I3 minus and water. And here what about I2? I2 is the non-polar molecule. So definitely there is no, like so LTF is only there. Okay. In between I2, its LTF is only there, non-polar molecule. So it's an induced dipole. It is an induced dipole. Interaction is between I2 and water. So no need of writing, just concentrate this one. Ion dipole interaction is the interaction which is present in I3 minus but not be in I2 and water. Okay, so this interaction, this strong ion dipole interaction is making I3 minus is more soluble in water, okay, than I2 minus. That's all about that question. I hope you understood. We can come back with the next question. Bye.